Yeah, so u minus f is u intersected with x minus f. So my goal is to show that this is open. Does anybody want to tell me why? Maybe somebody different. Pretty sure that Mackenzie and Zane have it, and it was Alice's idea.
Alice had it.
And Alex is in a different world over there, so I can't call him. Do you know why this is open?
Because by definition of a closed set, f is equal to x minus u, where u is the open set.
Okay, so this set here, is this open or is it closed?
Is open.
Because f is closed, so the complement of it, this one is open, right? And u is also, by assumption, open, right? So we're doing an intersection. So you guys remember this? An intersection, now you cannot take an arbitrary intersection, but we're only doing two sets here. If I intersect two open sets, I get an open set. Exactly. That's basically what you were saying, right? So we end up with an open set. Okay? Great, so that's the first one. Very easy, actually. Very short. This is the kind of thing I could put like in the in-class test, and I would hope it would only take a couple of minutes. It's not too bad. Okay, the other one is the kind of the reverse situation. So we're going to try to show that if we take the set F, we subtract the u from it, that we have a closed set. So if I want to prove, let's see, where is that on my picture? That's actually going to be right in here, right? I want to show that that is closed. Does anybody have a suggestion how to do that? How do we usually show that something is closed?
We need to show it can be written as the whole space minus an open set.
Right. We look at the complement of the set should be open, right? The complement of the set. So what do we get? If we take x and we subtract the set f minus u, we would like this to be open. If I can show that's open, then my set is closed that I'm looking at. So what is that anyway? Well, that's going to be everything outside of this shaded region. Sorry, let me get rid of this shading here. So if I take the complement of what is currently shaded in, what am I going to get?
X minus f. Enter.
X minus f, like that. So x minus f would actually be just out here a little bit, right? I mean, it would be all the stuff in the white space, but it wouldn't get this part.
Union.
Okay, so I need to add a little bit more.
Union intersection of f and u.
This would be the intersection of f with u, right? That's going to be a problem though, because we're intersecting an open set with a closed set, so I don't know what to make of that. Yeah.
Can you just rewrite f minus u as
This one? Oh,
yes.
this one. Yeah,
Yes.
okay. Let's try it a little different way. Go ahead.
that as x minus, so x minus. F minus u is going to be f intersection of x and x minus u.
Like this, right?
Yeah.
Yeah, so if you just think about the subtraction of sets, right? Anytime you take A minus B with sets, it's really just A intersected with the complement of B. That's just always a formula, right? We actually use that formula even just right here on the first part. So it's kind of what Alice is suggesting is we just kind of do that with this F minus U piece right here. And so this is perfectly good. And now this is the complement of this intersection. So, well, we're trying to show, so, this intersection is closed, right? Because F is closed by assumption, and X minus U is also closed, and I'm doing an intersection of two closed sets,
Which is closed.
which is still closed, so this whole thing is closed, and then the complement of the closed set is therefore open. And that means that, in other words, the complement of the set that we want to be closed is open, so therefore F minus U is closed in X. Okay? It's really just playing with complements a little bit. This formula at the top is good to remember. We use that quite often. So I just wanted to remind people about closed sets. Just kind of review the relationship between open and closed. Remember that open sets are closed, I should say, open sets are preserved by finite intersections or arbitrary unions. So any unions whatsoever. Doesn't matter, don't get caught up in what the index set is or anything like that. It's just any union of anything is always, of open sets is always still open. If I take a bunch of open sets and if I make a finite intersection, I have finitely many sets that I'm intersecting, then that stays open as well. Okay, but it doesn't work for infinite intersections. And then everything I just said is reversed for closed sets. So if I take arbitrary intersections of closed sets, they're going to stay closed. But if I have a bunch of closed sets and I take a union, it has to be a finite union of closed sets in order to stay closed. Okay, let's do an example. This is going to be good practice. I'm going to give you a bunch of sets, and I'm going to ask you whether they're open, closed, both, or neither. Because remember, it could be both, could be neither. Let's practice a little bit more, okay? So open, closed, both, or neither. And if you've done the practice quiz that from week 4, I believe, I have some of these on that practice quiz. So here's the first one. I'm going to take Z, that's just the integers, and I'm going to consider that inside of, here's my underlying metric space. So I would like to know if I take the integers, the set of integers, does that form an open subset, a closed subset? Is it both, or is it neither? So actually, before, don't blurt out an answer yet. I'm going to let everybody think about it for a minute, and then we'll go from there.
I have a question.
Yes?
So we normally say that a set is open in another set. So
Yeah, so that's what I'm basically trying to tell you.
we're saying
So Z is sitting inside of the real numbers under the absolute value metric. So I'm just using the familiar absolute value metric here on the integers. And remember, guys, if I used the discrete metric, everything would be open and closed. It would be both, and we wouldn't even think about it, right? If it's the discrete metric, because then singletons are open, everything's open, and therefore everything is also closed. But here I'm using the absolute value metric, so it's a little different. How many people think they know the answer here? Let's wait till we get a few more. We've got about 3 hands out of 8 so far. I'm going to give everybody another minute to think about it. Actually, if you get the first one done, just so you're not sitting there bored, I'll give you the second one as well that we're going to do. We're going to do the rational numbers second. So if you figure out the integers, then we'll do the rational numbers. Okay, let's look at part A. How many people think that the integers are open in the real numbers? Okay,
I
not,
think it's open.
you do, okay. So we have one vote for open. How many people think the integers are closed? Okay, about 4 of you. Now how many think it's both?
Oh, well, I don't know.
I haven't gotten to that answer yet.
Okay.
What about neither?
I think it's both.
You think it's both, okay. Okay, so guys, because you're doing the real numbers with the absolute value metric, your open sets are just open intervals. Remember guys, open sets are unions of neighborhoods, and in this case, a neighborhood is just an open interval, right? So, is the integers looking like a union of open intervals? I mean, an interval, right? Like, you know, you're going to be writing something like, an interval is going to be something like this, yeah? That's not going to stay inside of Z, right? These dots, these integer dots are, I mean, when I think of the integers, I just think of a bunch of dots, right? That are right here. And the question is, if you draw a little neighborhood around one of these dots, does the whole space between the interval of that you created stay on the dots only?
No.
It doesn't. So it's not open. It can't be open, right? No neighborhood, I don't care how small you try to make it, is not going to just hit only that dot. It's going to catch some points that are on the left and right side of that dot as well. Right, so this is not open. Now, when I'm asking if it's closed, I'm just going to look at what is not the dots. You literally want, in your mind, you want to just imagine deleting the dots from the picture, and imagine that you decide to come stand